Assalamualaikum and good morning, good afternoon or good evening to students BEKM from FKE UTEM taking BEKM 4751 laboratory, and this is the part where we simulate robotic motions using the Coppelia Sim software. So go to the Coppelia Sim, open it up, and you will see the Coppelia Sim education software, which has the scene where we can place objects or robots. We also have the scene hierarchy. The list of the objects will be placed here, and we have some menus on the top here and some icons that can help us in simulating. So first of all, let's open up a file. Let's open up a scene. So go to File and open a scene. And this scene should be the one that we're going to use for the lab, which is Part C_G1 scene. So when you've opened up this software, this program, you will see an arrangement of components on the scene, which consists of the robotic manipulator, the MTB robot. We also have the conveyor belt, and we have several other objects which are large blue and red boxes, and also small blue and red boxes. Alright, so on the bottom right of this scene, you can see a small axis of X in red, Y in green, and Z in blue. And this scene depends on this world coordinates for this location. So if you rotate the view using the center mouse and moving your mouse, you can see that the axis also changes with that. So never mind that. Let's go and try to explore how do we know the locations of each object. So when you click on an object, for example this blue object, small blue box, you will see the X and Y values location with respect to the world frame. Alright. So if you want to go to more detailed value of that, go to the item shift icon and you will see this small menu popping up. Go to the position and you will see the rectangle blue of X, Y, and Z coordinates according to the world frame. Alright, so let's try to simulate this robotic motion. Just go to the play button on top here. Click on it and you will see that the program starts and it moves to a location. And it tries to grab the object and places it in the wrong location. So let's try to run it again and pause when it reaches or tries to pick up the object at the wrong location. Okay, so you notice from this location, you can see that the command from the robot is 60 degrees of joint 1, 91 degrees of joint 2, and it reaches a position which is wrong. So where is that position? Just go to the MTB robot in the scene hierarchy, alright, and go to MTB axis 4H0. Alright, you can see that the location of the pick up position is at X minus 0.6832 and Y minus 0.5986. For a closer look to that, just open up the item shift and you can see the exact locations of minus 0.68322 and minus 0.59860. Alright, so that is the wrong position. It should actually pick up the object, the blue rectangle, at a different position. And how do we know that? Just click on the small blue rectangle. Alright, and you can see that there are locations of X, Y, and Z. X minus 0.187, Y minus 0.56, And for a closer look, just select the object shift icon, and you can see the actual locations here. So let's try to open up the program that causes the robot to move, or the commands that we can give to the robot. So you just click on MTB robot H0. There is a file icon right beside it. Click on that, and you will see a non-threaded child script of the MTB robot. Alright, I will go to straight away the lines that causes the robot to move to the wrong pickup location, which is this line, line 24, move 60, 91, 0.025 and minus 151. And also this line number 28, move 60, 90, 0 and minus 151. Okay, let's analyze the wrong location of the pickup point that the robot goes to. But before that, we need to know where is the robot located. Just go to the MTB axis 1H0. This will give us the location of X, Y, and Z of the first joint, which is actually the robot base or robot frame. This is where the robot XY axis is located. So it's important to know this. X is misplaced or displaced minus 0.8 meters from the world axis, and Y is exactly the same at 0.0. Okay, let's try to visualize the location of the robot and the wrong pickup locations. So we have the world frame, which is at 0, 0. Okay, this is the origin. This is evident, or we can see it from the bottom right part of the scene where you have x-axis and you have y-axis. Alright, and the robot at joint 0, or the robot base, is displaced at minus 0.8 from the world frame. In other words, the robot with its own axis at joint 0, it is minus 0.8 away from the world frame, and we have the robot frame axis of x and y, which is different from the world frame. The x-axis is opposite of the x-axis of the world frame, and the y-axis is opposite of the y-axis of the world frame. And the conveyor is placed in another location. And where is the wrong pickup location is approximately here. And you can see that when the robot moves to that location, the wrong pickup location, as we have investigated before, has XY values of minus 0.6832 and minus 0.5986. So try to look at X, which is minus 0.6832. The robot frame is at minus 0.8. So that gives us a difference of 0.1168. Or this wrong pickup location is to the left of the robot, which is minus 0.1168. From the motion, we can try to analyze the forward kinematics, which is the XY locations that comes from motion from joint 1 and joint 2. So by referring to the diagram on the top right, we have joint 1, which is angular rotation. Joint 2 is also angular rotation. Joint 3 is linear motion up and down. And joint 4 is the angular grip of the end effector. Additionally, in this diagram, you can see there is L1, which is the link length from joint 1 to joint 2, and also L2, which is link length from joint 2 to joint 3. So these parameters are required for the forward kinematics. Right, from the program that we've seen earlier, there is a command move 60, 91, 0 and minus 151. So the 60 degrees is actually the joint 1 angle, and the 91 degrees is the joint 2 angle. And this results in an XY location, which is the wrong pickup location. And again, the 60 degrees is located here, and the 91 degrees is the second joint, or joint 2. And if we go through again, the world coordinates are as shown on the bottom right of the scene, and that means the world frame is over here, and we have world coordinates previously found out was minus 0.6832 and y coordinate of minus 0.5986. So these coordinates can actually be obtained from the forward kinematics. That is from the robot coordinates. So look at x. This is minus 0.6832 from the world frame. But actually, from the robot frame, it is just minus 0.1168. And this is obtained from x equals to L1 link 1 length cosine theta 1 plus L2 cosine theta 1 plus theta 2. This gives us the x coordinate of the wrong pickup location with respect to the robot frame, which is minus 0.1168. And for the y coordinates, according to the robot frame, that is L1 S1 sine of theta 1 plus L2 S theta 1 plus theta 2. If we put in the values here, we get 0.5986. So again, L1 is the link 1 length, which is 0.467 meters, and L2 is 0.4005 meters. And you can see that y is positive 0.5986 because according to the robot frame or robot axis, it is positive. But according to the world frame, it is negative. That's why our world coordinates gave us a negative 0.5986 value. Right, now we're going to refresh our knowledge on inverse kinematics, which is finding out joint 1 and joint 2 angles from the end effector or gripper xy coordinates. We know xy, and we need to find theta 1, which is the angle at joint 1, the shoulder angle, and also theta 2, which is joint 2 angle or the elbow angle. Right, so we know xy or Cartesian coordinates of the end effector, which was previously given as negative 0.1168 and 0.5986, which are the gripper locations based on the robot frame. And we need to calculate joint 1 angles and also joint 2 angle from the xy coordinates. So how do we do that? We'll solve for theta 2 first, or joint 2. The first step is to determine the initial parameters or constants needed. There are 4 parameters needed, which is x and y, the xy locations, and also the length of link 1 from joint 1 to joint 2. What is the length here? And also length of link 2 from joint 2 to joint 3. Second step is to calculate cosine of theta 2, and that is obtained from this formula. C2 equals to x squared plus y squared minus L1 squared minus L2 squared divided by 2L1 L2. And by putting in the values, we'll get negative 0.01744. And the third step is to calculate sine of theta 2 or S2. That is simply from the square root of 1 minus C2 squared, and that could be plus, it could also be minus. So we have plus 0.9998 or minus 0.9998. And step 4 is to obtain theta 2. That can be done by using the arctangent function of S2 over C2. And if you put the positive value of 0.9998, we'll get positive 91 degrees. Or if we put negative 0.9998, we'll get negative 91 degrees. And so we've solved for theta 2, which is joint 2 angle. So let's proceed to solve for theta 1. And we can do that by firstly doing the initial parameters identification. These are exactly the same as we did for theta 2 before. And next is we calculate a new parameter, which is K1. And that is from this formula equals to L1 plus L2C2. By putting in the values, we will get 0.46001. Step 3 is to calculate K2, another new value. So there are two possibilities because we have two possibilities of S2 sine theta 2 in the previous theta 2 identification. So that is K2 will produce 0.4004 or minus 0.4004. And step 4 is to obtain theta 1. This can be done by using the arctangent function from arctangent y over x minus arctangent K2 K1. And if we put in the values that we have earlier according to the robot frame, we will get theta 1 equals to 101.04 minus 41.04 or 60 degrees. This is with respect to the robot base. And if we try to visualize the position or orientation of the robot, it is as shown as in this diagram. That is for a positive 91 degree of theta 2. But if we have a negative 91 degrees of theta 2, that will result in a different value, which is 101.04 minus negative 41.04. That gives us 142 degrees of theta 1. If we try to visualize that, the robot is in a different orientation configuration, which theta 1 is 142 degrees and theta 2 is minus 91 degrees. Both of these orientation arrive at the same pickup location, but again is from a different approach. Okay, so let's try to simulate the motion again. We want to find out where the actual pickup location should be, and let's click the play button for that, and let's pause it at this moment, and we'll click on the object, which is the blue object, and we can see that the location is as shown. It is minus 0.187 and minus 0.5612. So this should be the location that the robot has to go to pick up the object. Okay, so let's try to find the correct pickup location. And the first step is to determine the initial parameters or the constants needed for our calculation. So the roll frame is 0, 0 as known. And we know that the robot is at that location. It has its own robot axis. And the location of the pickup should be at the blue box. If we click on that, as done in the simulation, we find it is minus 0.187 and minus 0.5612. So what that means is that from the world frame it is minus 0.187, but from the robot axis it is actually minus 0.613 because the robot base is at minus 0.8, and for y-axis it's just positive 5612. So we have found out the pickup location of the robot, which is minus 0.613 in x coordinate and 0.5612 for the y coordinates. So next we need to find the joint 2 angle, in which we can calculate firstly the cosine of theta 2, and by putting in the values in the equation we'll get cosine of theta 2 is 0.8347. And for step number 3, we calculate sine of theta 2, that is plus minus square root of 1 minus c2 squared, and we'll get plus minus 0.5507. And lastly, for step 4, we can obtain theta 2 by using the arctangent function s2 over c2, and that gives us 33.41 degrees. Or it could also be minus 0.5507, 0.8347 arctangent, and we'll get minus 33.41 degrees. So notice the magnitude is 33.41 degrees. Let's go to join 1 angle now. And firstly, to determine the initial parameters, and we have found that out before, and we calculate K1, which is from the formula will give us 0.8013, and for K2 we'll get 0.2206, but it could also be minus 0.2206 coming from the negative value of S2. And lastly, in step 4, we can obtain theta 1 by calculating the arctangent according to this formula. And if we put in the values for the first set, which is K2 positive, we'll get a value of 122.14 degrees. But if theta 2 is negative 33.41, our K2 will be negative. And in that case, we will have theta 1 is 152.9 degrees. Now that we found theta 1 and theta 2, let's now change the program by inserting the values into the 2 lines that affect the pickup location. So first of all, open up the program file, which is next to the MTB robot object, and then replace 60 and 91 at lines 24 and 28 with the values that we have calculated just now. That was 122.13 and 33.14, 122.13 and 33.14. Okay, just close the program and let's try to run it by clicking the play button to start the simulation. So what we can see from here is that the robot successfully grips the object, the blue object, and if we run the simulation, it will try to move it to a new location. Great, so we found out the location for the correct pickup, and we have actually simulated it. We have seen that the robot grips the object correctly, and now why not you try to find out the location of the drop of the box, or the place location, which should be on the blue rectangle, large rectangle or object, and you can use the inverse kinematics formulas that were shown and follow the steps, and later try to change the program by adjusting the values of join 1 and join 2 in the program file, which is at lines number 30. So this minus 60 and minus 91 should be changed to a new value that you have found, which is the value that is on the blue large box or platform. Okay, all the best. Good luck and enjoy your simulation.